moving on, we continue the session with our next talk that is titled Preliminary Security Analysis, Formalization and Verification of OpenTitan Secure Boot Code. It's presented by Anton Christensen from Aalborg University. Please, Anton, you should be able to share your screen and go ahead.
Thank you. Yes, so this preliminary security analysis for OpenTitan in collaboration with some fine people at Huawei and myself, my supervisor, and a few others from Aalborg University. I'm a PhD student at Aalborg University. So to begin, let's talk a bit about the scope of the project. So we're working with a project called OpenTitan, which is an open source reference implementation by Google and ETH Zurich, among other like industry partners, for implementing a silicon root of trust, which for the most part is, or in simplified terms, is hardware device based on a RISC-V core with several security-related peripherals such as HMAC, hashed message authentication modules, a separate entire core for doing big number calculations on 256-bit numbers for different cryptographic operations and such. And in general, it's a repository that's full of Verilog code. They use Verilog to describe the entire system, and they provide a lot of documentation that tries to describe different scenarios in which this can be used. But in general, it's quite well specified for the hardware, but the software stack is more vaguely formed, and there's little in terms of full like software implementations of the initial bootloader stages, which I think they have plans for, and that we at least would like to see. So for our case, we've needed to implement ourselves the first boot stage, or at least follow their pseudocode to achieve something that's more well specified, such that we can model it. So here's an example of how they suggest the system can be used in like a software stack manner. In general, like the idea is you want to give securities from the manufacturing stage, so from the silicon creation stage up towards the different people who will be handed this chip before it goes out to a consumer. So you will probably have a manufacturer write a ROM that can then load a boot stage that is securely authenticated, and the higher bootloader layers will be created by, for example, an OEM, which will handle securities in order to run applications on like a user space layer. But for our case, this is basically the overview of the OpenTitan platform as will pertain to the project. So what we want to achieve is we want to demonstrate a way of analyzing the security of a secure boot method of getting from the initial boot stage to the subsequent one, however that be a application or a further bootloader. And of course that pertains, we need to describe the properties of the system, and then we want to model it and make sure the model has those properties, and then of course compare and contrast with whatever system implementation eventually ends up with. So it's somewhat of a showcase of how good software modeling can be used but we suggest it should actually be used before the implementation, whereas we've gotten an implementation handed to us that we're trying to analyze, but this should work in either case. So the tools we'll be using is two different modeling tools. One is UPAL, which is a well-known model checker from Aalborg University. That, of course, the people at Aalborg University are quite familiar with, and it has the nice feature that it is especially good for timing-based properties. And we also tried to contrast it with another modeling tool called CBMC, where the modeling formalism is annotated C programs, whereas UPAL is very graphical automata with signals and guards that communicate between the different models. These only, though, cover mainly one of three of the major branches of formal methods. And so this study mainly covers the strength of model checking, and it will be clear in our conclusion that model checking doesn't do every job of security. When doing security, you really want to involve different formal methods approaches in order to cover different types of properties. But we'll return to that maybe later. So as mentioned, there's not a lot in terms of actual implementation of secure bootloader from the project itself. So we went ahead and created one from the descriptions there was in the documentation. But to simplify this view a little bit, I've created a further simplified version. So the general idea is the ROM should read a manifest of whatever software stage comes next, and it should get a signature from that manifest and different properties about how it should be loaded. Then it checks the signature, and if the signature is invalid, then of course it handles that in a secure way, probably a secure shutdown. And otherwise, we use the physical memory protection module to allow actually executing code in that memory region, and then of course jump to that memory region. And should it ever return to the ROM stage, then we need to handle securely shutting down and maybe marking an exception of some kind. So that's the general idea of the secure bootloader we're working with. Then the analysis is made up of 3 levels. We call them policies, goals, and properties. Policies are the very high level descriptions of the system and the ways it should work. Goals become more specific and can attain to specific components of the system, whereas properties are detailed enough that they don't really make sense before understanding the specific model implementation. So they will be specific to each modeling formalism. Properties can be such as these, that the mask ROM, the initial ROM stage, must only execute code that securely transfers execution to a verified ROM extension or terminates, or cryptographic material and other secrets must not be leaked. Very vague statements that need to be specified further. And so we have the goals, such as for access right must be configured correctly. What does that mean? Well, it means that writing to a memory section requires that you have writing privileges. And of course, even further specifying that means that the physical memory protection module must be in a state where that allows it. So we see here some of the properties for executing a memory section requires execution privileges. Well, then in CTL of UPAL, we can express the properties that for all paths at all states, the PMP module must not be in a bad execute state, or there must exist a state on some path where the PMP module is in a good execute state, where you are allowed to execute the memory region of the bootloader section. So of course, this is an example of how that's implemented in UPAL. The modeling language is I kind of need to point out, I'm not sure if you can see my cursor, but basically this models the hardware system of the PMP module, and not just the software formalism on its own. But of course, we can check on these states and with the association of the CTL statements, we can then ask queries on these objects. On the other hand, CPMC will let you describe C code, which is probably a stage in the development of the RTL in the first place, where you'll create C models of however things are supposed to work. So generally, our experience is that we're able to do this analysis and cover most of the goals that are listed. Most of the goals for a system such as secure boot is quite data flow oriented, and properties such as does the decryption algorithm work correctly, or is that implemented correctly? It becomes very difficult to do in a satisfying way with model checking. But assume under the assumption that such things work, we have a good basis for trusting whatever implementation that follows the model. So the general idea is for these kinds of properties, we've definitely gained the experience that they are well covered under model checking, but model checking itself is not sufficient to really catch all these aspects. But we are surprised by how easy it is to perform co-verification, where we both model hardware features of a language that we have little experience with, such as Verilog, and combine that with models of the software. And as an example, we have from the RTL code of the HMAC module, where we discovered a vulnerability in the implementation. So this is from the HMAC module, where it's a description of the logic that says when the clock goes high, or there's a negative edge on the reset line, we handle the reset, of course, if the reset is low. But otherwise, if there's a write to this wipe secret flag, then the secret key used in the hash-based method authentication signing process gets overridden by the secret key XORed by 8 copies of this wipe value. And if we go to the description of I just looked up the documentation for today from the OpenTitan project. There's basically memory mapped IO. So there's a register called wipe secret, which if you write to, the CPU writes a value into the register. If the value is used to randomize internal variables such as secret keys, internal state machines, or hash values. So this sounds like it's supposed to render basically the internal secret keys unreadable after this or unusable in some way. But for choosing a bad value for wipe, for instance, if you simply choose 0, then the secret key is untouched, or even no matter what value you choose, the secret key is recoverable through basically calling the function again or writing to the same register again with the same value. So a typical use of the HMAC module might be something like this, that I want to create a message authentication key for some message. So I write my secret key that I need to be careful doesn't leak anywhere. And then I write all the data of my message to the module and ask the module to sign it, wait till it is done. And while I'm waiting, I might let the operating system get back control and let some other process run. And then when I'm done, I might read the signature out and then call wipe in order to assure that that no one can sign messages with my key. But of course, this presents the problem that there might be some way of using the system, especially if we're in a multi-threaded environment, or we are doing scheduling, or the operating system is scheduling another process in here. In that case, someone might wipe with whatever value that's not really supplied here. And if they use the same wipe value, which is only 32 bits instead of the keys 256, then the security of the key has basically been lowered by many orders of magnitude.
Anton, sorry to interrupt you. There's
yeah.
only a bit over 1 minute left.
Okay, I'm done in just a moment.
Okay.
Good. Thank you. So basically, we can model this in both CBMC and UPAL through a simple like Doleviao style attacker, where in CBMC, as we haven't looked at that much yet, we can make a non-deterministic choice and just let it perform any of the operations on the HMAC module that we've seen, and it shows that simply picking that value, that definitely generates the right key, and then a separate process can sign messages with our key without having access to the key, but simply by guessing this wipe value or knowing it in advance. Same is simple for UPAL. These kinds of attacks are easily modeled. Yeah, so that's our main findings. The finding of a somewhat simple mistake, which is there's of course still time to fix, because it's an open source project. So we have taken contact to OpenTitan and talked about this. But yeah, I think that's my talk.
Thank you very much for the talk. Very interesting. So if you have questions for Anton quickly, maybe you have time for 1 or 2 questions to
Sure
use
thing.
the raise hand button in Zoom. I don't see any question right now, but in the meantime, I can ask quickly a question. So the title of this work is Preliminary Security Analysis. Do you plan to continue working on this, or?
Not immediately, but in future, and there's definitely work in this direction. We are probably we have plans to work on the same project, like keep analyzing OpenTitan in a broader context with different formal methods tools to really get an experience of how a big system like this can be analyzed through and different problems being discovered in that way.
All right.
Yeah.
Yeah. Just also a quick comment from the chat section. Simin, I might butcher this last name. I'm very sorry. Nadiem Tehrani. It's commenting that P3 should read may not be leaked, and instead of must not be leaked. Just I think a comment from your presentation.
Yeah, that must be a P3 property. Yeah. A lot of the work on the formalization of the security analysis have been discussed, but we've tried not to change them too much from how they initially looked, because they needed to work across two teams that both worked with these separate tools. But yeah, I get your point. Thank you.
Right. Okay. Thank you very much. I think we're running out of time, we ran out of time already. But thank you very much for the presentation. That concludes this second session.